All right, in the previous class, we have seen that in the operation of a helium neon laser, helium serves as surrogate species, while neon performs the role of light emitting species. Let me very briefly explain to you once again today as to why helium is required to be used in the first place in the operation of neon laser, because helium is not the light emitting atom. Well, for this, we begin from a qualitative representation of the low-lying energy levels of both helium and neon that participate in the process of lasing. So let us begin with helium. This is the helium ground state. That is basically the electronic energy state with N equal to first orbit electronic orbit. That is the ground state. And the first excited state electronic energy of helium, which is N equal to 2, it actually, as we have seen yesterday, splits into two sublevels, and they're denoted as 2 is 0 and 2 is 1. And this splitting occurs because, as we have seen yesterday, electron, as it rotates, it has, of course, an orbital angular momentum, and because it also spins about itself, it also has a spin angular momentum. Because of that, this level is split into two sublevels. These are the spectroscopic notation to denote this energy level spectroscopically. And let us not go into detail. Most importantly, the space between this ground state, first excited state, is devoid of the presence of any other energy level, because this is the first excited level and this is. Now let us turn our attention to neon. So this is the neon ground state. So basically it is the ground electronic state which is first orbit n equal to 1. And interestingly, neon offers multiple lasing transitions originating from two upper laser levels and two corresponding lower laser levels. Two corresponding lower levels. The upper laser level, this one, is the fourth excited electronic state of neon, which is therefore the fifth orbit, n equal to 5, and this is denoted as 4. Sorry, this is n equal to 4, n equal to 5, fourth excited. So this is 5 S, and this is the third excited state, meaning this is the fourth electronic orbit, and this is denoted as fluids. So these are the upper Lissel level 1, upper Lissel level 2, and these are the lower Lissel. So this is actually the third electronic excited state, which is denoted as 4p. So this is n equal to 3, n equal to so this is the third, so n equal to 4, third excited state, n equal to 4, and this is the second excited state, so n equal to 3, it is denoted as 3p. There is yet another level, this is the another second excited level, which is denoted as 3s, which also participate in the lasing process, but I will come to its role in a while. And of course, because this is the second excited state and this is the ground excited state, there will be other energy levels belonging to the first excited state, that is n equal to 2, located in between in this space. Now, assume that you have in your laser gas contains only neon and no helium. That means essentially you have this laser discharge tube where you have only neon atom. Of course, you have created a discharge, and there is, of course, present electron of varying kinetic energy. Now, if this neon atom in the ground state, collides with the electrons varying kinetic energy, that is velocity in the discharge, then you cannot selectively transfer the neon atoms from the ground state to any one of this upper state, that is here or here, selectively. That is ruled out, because there will be many collisions invariably transferring the neon atoms from ground state to the lower energy levels as well as the other levels which lies in between. In fact, the probability of populating these levels may actually be more than these levels. So it is absolutely improbable that you will strike a population inversion between these levels, upper laser level and lower laser level, either of them, in a discharge containing only neon atoms. I hope you have realized this point pretty well. In contrast, you see, helium energy states, look at this excited states of helium, first excited state. This is absolutely quiet. There is no other energy level in this space. So now if a helium atom ground state collide with electron of varying kinetic energy, then invariably the atom from the helium ground state atom will be transferred to either this or this. So this will be helium in 2s0 plus electron of less kinetic energy, because electron has supplied the kinetic energy required to transfer the helium atom from the ground to this state. So the electron will move with correspondingly lower kinetic. And also helium at the ground state will collide with electron of which is having appropriate kinetic energy, and also will transfer it to helium, other sublevel 2s1 plus electron with less kinetic energy. Of course, the energy levels, the other excited energy levels of helium, which are located up, would also be populated to some extent. But you need electron, say electron distribution, energy distribution, velocity distribution would look somewhat like this Maxwell distribution. So to populate this level, you will need electrons with correspondingly higher energy, higher velocity. And the number of, this is the number of electron with velocity v, and their number reduces as the velocity increases. Therefore, they will be populated, but not as much as these levels. So, if you look at this, the collision of helium with electron will invariably bring a large number of helium atoms from the ground state to this level or this level. Now let us turn our attention to helium, to neon, which also is colliding with electrons in the discharge, but would not be able to selectively populate the upper decile and maintain a state of population inertia because of the problem that I just explained. However, the helium that has been, say, let us consider helium that has been excited to this level. So helium in this state, if it now collides with a neutron, with a neon ground state, then because this energy level and this energy level, there is a close match. They are almost same energetically. Therefore, this collision, the helium will transfer its excitation energy, this excitation energy, to neon, and neon will receive this energy and will climb up to this level. And the helium will of course come down to the ground state. So then this is going to be helium will come to the state, and this energy will be transferred to neon, and neon will climb up to its first upper blazing level. And likewise, if the helium in this sublevel collides with neon in the ground state, the collision will also result in helium coming down to the ground state and transferring this energy of excitation to neon, bringing it up to this level. So neon will come to the second upper level. And by appropriately uh, mixing, appropriately varying the concentration of helium, varying the concentration of helium in the helium-neon mixture, significant number of neon atoms can be made to populate upper laser level and lower level, the two upper levels. And thus, we will be able to create population inversion in the mixture. In fact, for an optimum operation of helium laser, the concentration of helium is 5 times that of helium. So majority of the gas is actually helium. So now you have understood why helium is required. It works as a surrogate gas. Without helium, you would not be able to create population. And so there won't be any lasing. So then, the other aspect is that as these levels are very close match, so as we just discussed, as the excited helium atoms collide with ground state neon atoms, near resonant exchange of energy takes place between 2s0 and 5s and between 2s1 and 4s. This cross-section of such reactions, collisions are very, very high because the energy of these two states being equal. The slight mismatch of energy between these two will be compensated provided by thermal energy that is always present in a gas at finite temperature. The thermal energy is omnipresent except when the gas is at absolute zero. So then, the transfer of energy from helium to the energy states of neon begins the process of lasing because you have now created population inversion, so the process of lasing will begin. You have to place, of course, your active medium inside an appropriate cavity. I'll come to this in a while. Now, population inversion actually occurs here on several transitions, both infrared at two different wavelengths, 3.39 micron and 1.15 micron. This transitions basically occurs between, this is, we have called it upper laser level 1, and then this is lower laser level 1. So between this level and this level, there is a transition, infrared transition, which occurs at 3.39 micron wavelength. Then between this level, that is upper level 2, lower level 2, it gives this transition gives a photon at wavelength 1.15 micron, and there is a visible transition also which occurs between this level, upper level, and this lower. And this actually results in this is again split into number of sub-levels for the same reason, because the electron has both orbital angular momentum as well as spin angular momentum, and number of transitions, visible transitions actually can result from this emission, which can be red, orange, green, and yellow. Now the transition at 1.5 micron has the highest gain. And therefore, it is not surprising that the very first helium neon laser operated on this infrared light at 1.15 micron. That is because intrinsically this transition has the highest gain. However, how do you bring any other transitions into lasing? Because as you can see, number of transitions are possible. So this has the highest gain. So on itself, lasing will occur on this transition. But how can you bring other transitions into lasing? Well, this is possible by introducing selective losses to other competing transitions, which is readily doable with proper selection of cavity mirrors. Well, let me very quickly elaborate on this. Suppose, so this is my wavelength, and let me just show the gain of different transition in a very qualitative. So first is the visible transition, which is the red light, which works at 0.6328 micron. Then the next is 1.15 micron, which has the highest gain. This is basically gain, and this is wavelength. So this is gain. This is 1.15 micron. And the next is 3.39, which has an intermediate gain. 3 intermediate. Now suppose the loss that the cavity offers on these wavelengths are same for all the wavelengths, and therefore the loss line can be represented in this gain curve by a straight line. And suppose the loss is such that it can be represented by a straight line. This is the loss line. This is the loss line, which is parallel to this wavelength, because it is independent of the wavelength. Suppose our cavity is such. Now see, for these lines, this visible transition and one infrared transition, gain actually lies below the loss line. Therefore, we now know that the oscillation or amplification of light will not be possible in these two transitions. Cavity would not support these oscillations on these two lines because the gain here is less than the loss. However, this high gain line, 1.1, gain for this line, gain exceeds loss. Therefore, lasing will set in alone on this transition. This transition will be to laser. So the first laser that operated most probably presented such a scenario where the lasing occurred on this infrared line, which is the highest gain. Now the question that arises is, how do we get lasing on other transitions as well, which have say much lower gain? So say this is our active medium, that is the helium gas discharge. We have created population inversion within the transitions that neon actually offers. Of course, helium has collided with electrons in the discharge, then it has got excited, then that excitation has been transferred to neon, and eventually you have created gain. Now you will have to, of course, place it in a cavity. So let us assume this is our rear mirror, which is 100% reflective, and it is concave to add stability to the cavity. And the output mirror, or the partially transmitting mirror, is so chosen or so designed, this is a dielectric protector, that the line with the highest gain, so 1.15 micron, has the least reflectivity, that is, suppose its reflectivity is 10% at 1.15 micron. And this line, 3.3 micron, suppose it has, this is very qualitative values. I'm using them only to explain to you that how you can make the laser laze on other conditions which have lower gain compared to infrared, high gain infrared condition. And so this is that 3.39. And suppose the visible light, which is the least gain, we provide very high reflectivity. These are the reflectivity at 0.6328. So you see, for the high gain line, the reflectivity, this mirror offers 10% reflectivity. So whatever light shines on this, only 10% is reflected. So 90% is lost. So loss for this is very high. And then this one, which has intermediate gain, also gives intermediate loss. 70% of the light is lost. While the lowest gain line has very high reflectivity. 90% of the light that shines onto it is reflected. So only 10% of this, that is 0.63 28 micron is lost. And therefore, if I represent this loss on this gain card, so this loss is now selective. Different transition has different loss. Suppose for this line, the loss line is located from here. And for this, the loss line is located here. And for this, suppose the loss line is okay. Now see, in this case, you see that glazing cannot occur on either this line or this line, although they have hard gain. Why? Because the loss of this line is much less, it will allow glazing to occur on this wavelength. And that is how, by selectively introducing loss to the transitions, you can actually make the laser laze on transitions which have much lower gain. And this is absolutely doable. The other point is that in the visible range, as I said, the strongest line is red line, while the other lines, like orange, yellow, green, they are very weak and understandably have no commercial value. So today I close here, and tomorrow we will continue with helium neon laser and see what are its possible applications.